So we said on this video we would talk about net change with respect to velocity functions and how that related to acceleration, velocity, and distance traveled. So if I'm looking at a problem like this, a particle's moving along a line, so its velocity is that crazy function in feet per second. So feet per second, that's an automatic rate, right? But we know velocity is the rate of change of distance over time. So when the question down below asks what's the particle's displacement on the time interval 1 to 5 seconds, that's really asking what is this integral from 1 to 5 of that yucky, gross, long function. And we're going to use our calculator, like I said, for at least for now. Yes, you should be able to do this one by hand, but we need to save some time for this video. And so we're going to calculate that based on our calculator. So let's keep in mind this is a velocity, so this one happens to be feet per second, and this is a change in time, and that's a variable. That's a variable part. That's why that differential, I keep saying, you really have to put because it's a variable in and of itself. So we get feet out of that. So this, when I do the calculations in my calculator, I get 10 2/3 or 10.3, 10.6 repeating, 10 2/3 feet I should get. So that's a displacement. So what's the difference between that question and the very next question? What's the particle's total distance traveled in that time? So to do that, I'm going to actually go to what you see as your first page, and then we'll come back to that. So on this page, on the second page here, I drew just a random velocity graph. This has nothing to do with the last problem. Please don't make it. If I want to find the displacement from some time to another time, and A is, say, here, and B is, say, here, this part is distance traveled forward because velocity is above the axis. Positive velocity means moving forward versus backwards, or left versus right versus left, I should say. So this is right movement. I think it says it's moving along a line, so we'll say it's left and right. And this is also right movement. That's left movement, though. So that's distance that the particle moved backwards, per se. So maybe this is, I don't know, 10 units, and this is 8 units, and that's 2 units. In total, the particle hasn't moved at all. I said that backwards. The particles moved 10, 12 forward to the right and 8 backwards to the left, so they've moved 4 total. If this were, say, 18, that'd be a different story. Now, the particle has moved more backwards. It's ended up 6 left to where it started because it moved 10 to the right, then 18 left, and then 2 right. So the displacement is just how far you are from where you've been. So that might be something worth writing down. Displacement is how far you are from where you started at time A. Distance traveled in this different scenario here where I have the 18 written in would actually be 18 plus 10 plus 2. That's 30. It traveled 30. So if I took the velocity function and made an absolute value out of it, I could get that answer. Okay, forgive my poor drawing skills. And then if I made that positive, finding that integral, now that would give me my 30. That is the total distance travel, and that is how you draw an absolute value curve, right? You make everything go above. So this stuff would go away. Now it would be above. So I can't erase the stuff that was on there before, so that's all right. All right, so this stuff is gone away, and it's now flipped above for the absolute value. So what I have drawn now in red is the absolute value of that velocity function. So it changes it a little bit, and it will give you all the distances moved and add them up, because that's what integrals do, right? This is a sigma. It's an addition sign. It sums up all the little rectangles. So if you make them all positive, the negative things that went backwards or to the left end up getting added on instead of subtracted off. All right, so going back, now we're going to flip. So we said on this video we would talk about net change with respect to velocity functions and how that related to acceleration, velocity, and distance traveled. So if I'm looking at a problem like this, a particle's moving along a line, so its velocity is that crazy function in feet per second. So feet per second, that's an automatic rate, right? But we know velocity is the rate of change of distance over time. So when the question down below asks what's the particle's displacement on the time interval 1 to 5 seconds, that's really asking what is this integral from 1 to 5 of that yucky, gross, long function. And we're going to use our calculator, like I said, for at least for now. Yes, you should be able to do this one by hand, but we need to save some time for this video. And so we're going to calculate that based on our calculator. We are going to see that the total distance traveled we do by taking the absolute value. Now, normally you would have to actually go on a graph and find every place where this function inside of the absolute value dips below the curve and break the function up. For what we're doing right now, we're going to say putting your calculator is good enough. That would not normally be acceptable, but for now and today, and for what we have to get through before our crazy AP exam, this crazy year, we're going to say that. So I'm going to pause. You're going to pause. Try putting it in your calculator. You can find that absolute value under ABS, under math, and it will look really nice in our new version of calculator, the math print version that your new TA 84s have. I, in fact, got 71/6, or in other words, 11 5/6 feet is the total distance traveled. So just because you ended up 10 2/3 feet from where you started at the end of second one, doesn't mean that's all the distance you traveled. He went backwards, this particle went backwards and forwards a little bit and actually traveled a total 11 5/6 feet in total. Ahead to this next example. So we're going to talk about it all together. So finding the average velocity on the same interval, and I'm going to change this one, by the way, in a second, just to make it less trivial. To find the average velocity on the interval, remember how we used to have to do change in position over change in time, or in our book we did it change in S. They could just call it S instead of X, but physics people would call it X. So change in position over change in time. Well, this isn't a position function. It actually is a velocity function. Remember how you used to try to velocity at the end and try to velocity at the beginning and add them together and divide by 2, and I kept saying, no, that's not the average velocity. Because you have to add up all the velocities on the interval, and there's an infinite number. So we now finally have a way to add up all the velocities on an interval, and we don't have the position function to actually do this formula. But we do have a way to add up all the velocities, right? That's what this sign means. It's a sigma sign. It's an add up sign. So we're going to add up all the velocities from 1 to 5, okay, and then divide by 4, because there's 4 seconds. So guess what? Isn't that looking a lot like the MVT for integrals? That is the mean value theorem for integrals. We have our fraction out front. That's 1 over b minus a, right? That's 5 minus 1. I just didn't write it. That's how I got 4 seconds on the interval. And then the fundamental theorem using the function. That is the mean value theorem for integral. And we can find the average, mean, value, mean, value, average, means, mean. That's the same thing. We can find the mean value, the average velocity, just using the mean value theorem. And so now this integral makes things really easy. So if I just, I'm going to write the actual function down, t to the third minus 10t squared, and you certainly should be able to use the power rule to actually calculate that, don't forget your differential because it is a variable, it is a time. And this seconds here, this 4 seconds times that 4 seconds, since that one's in the denominator, will cancel. And so you get a velocity back. You get an average velocity. If you do that in your calculator, don't forget the 1/4 part. You should get 2 2/3 feet per second. Now, we're just using our calculator to get that with integral, but that is definitely one you should be able to find the antiderivative by using the power rule, putting in the 5, putting in the 1, subtracting. It's just a lot of fractions and tedious for here. Now, I told you I'm going to adjust this. I actually want to do the integral from 0 to 2 instead, okay? And I want to change it because it turned out to be pretty trivial from 1 to 5, so bear with me here. So if I want to find the average acceleration, that's a little bit different now. Now I want to find the average acceleration. Now our old way, we said, just like before, was delta V over delta T, and I've got delta V. I've got V, so I can find delta V. So in other words, I have to do V of 2 minus V of 0 divided by 2 minus 0. It's just slope, right? Average acceleration is average rate of change of velocity. So we have to actually find the slope of the secant line. Well, if you calculate, if you put in 2 and you put in 0 to these, you get V of 2 was 6 minus V of 0 is negative 20, and divide by 2 minus 0. I did that, I got 26 divided by 2, aka 13. 13 what? This is meters per second. Oh, excuse me, it's not meters, it's feet per second, and that's 2 seconds. So that is feet per second, or feet per second squared. Now that's the old way we did it. But look how slick it is now that we can use what we already know. How do we find acceleration? Don't we just take the derivative of velocity? So thinking back to doing derivatives, now can you get your brain wrapped around derivatives now that we did antiderivatives? But you just get this using the power rule. Nice easy derivative. I took the 3 down, changed it to a 2, brought the 2 down, changed it to a 1, brought the 1 down, change it to a 0, and the derivative of 20 is 0. So that is acceleration. The derivative velocity is the acceleration function. That's it. So if I want to find average acceleration, we can do it just like we did above here. You can find the average of anything by taking the integral on that interval. And remember, I changed it from 0 to 2 instead of 1 to 5. It was pretty trivial. You can find out it gets you a 0, and that's why I didn't like it. But you have to do the average value. So you need that fraction out front for average value theorem. And then our function that we know is for acceleration. Sorry, that's not a 1, it just was a stray mark. Don't forget your dt because it is actually a variable, because this seconds and that second's going to cancel out to give you my acceleration right there. And when you do that, lo and behold, you have a 1/2. That's a 26, and you get 13 just like you did before. You're going to have to decide which one you like better, but I honestly think this one's really slick. It's really quick to take the derivative. It's pretty quick to take the antiderivative. If you had to do the antiderivative by hand, maybe the first way is better, but both are legit and they're both perfectly acceptable, and they will both yield the same answer. So what we did before, way back in semester 1, and what we're doing now, applied with integrals. And so now we can add up an infinite number of velocities, an infinite number of accelerations, because we have a way to add up, taking limits as n goes to infinity, an infinite number of little rectangles, or infinitely skinny rectangles, meaning basically adding an infinite number of those little heights under the curve. Isn't that fantastic?